Welcome to part 2 of our series on arithmetic sequences. You might recall from part 1 that an arithmetic sequence consists of either ascending or descending terms that have consecutive terms as a common value. Here we have our sequence 4, 7, 10, 13 and so on. And notice that each pair of consecutive terms goes up by 3. The first term we call a equals 4, we use the lowercase a, and the value, the common difference of 3, we call d equals 3, and of course our nth term is, as you can see, Tn equals a plus n minus 1 d, and we can see that at the bottom of the screen. That will be useful in a little while. For this particular sequence, if we substitute our values for a and d in our value for the nth term, we have Tn equals 4 plus n minus 1 times 3, and if we expand and simplify the brackets, we have Tn equals 3n plus 1. That gives us an explicit way of determining any particular term of our sequence. Now let's see if we can obtain some useful properties from our sequences. Now that at the moment might look a bit scary to you, but I'll try to explain what it means. We have LIM, which means the limit. Underneath that we have n approaching infinity. And then we have our numerator and denominator, Tn plus 1, and Tn in the denominator equals 1. Now, if we say that in a formal sense, we say that limit as n approaches infinity of Tn plus 1 over Tn equals 1. What we're asked to show is that the ratio of two consecutive terms of an arithmetic sequence is equal to 1 as the terms approach infinity. Let's see how we can do that. We have from our previous screen the definition of the nth term, Tn equals a plus n minus 1d. We can use that to work out the Tn plus 1 term by substituting n plus 1 instead of n. And you can see that we have Tn plus 1 equals a plus n plus 1 minus 1d. And that simplifies to a plus nd. What we can do now is to substitute those two expressions into our expression at the top. So we have the limit as n approaches infinity of the ratio of the two terms equaling, and we've made the substitution, so we now have in the numerator a plus nd and in the denominator a plus n minus 1d. And simplifying the denominator, we have a plus nd minus d. What we're going to do now is to see what happens to the terms in the numerator and in the denominator for large values of n. In other words, as n approaches infinity. Notice that in the numerator, for large values of n, and we mean perhaps thousands or even millions, the value of a, which is the first term, is a constant, and we can ignore that because its effect when n is very large will be insignificant. Similarly, in the denominator, we can ignore the values of a and d because they also will have negligible effect overall. So we can replace those with zeros, if you like, and what will remain is that we have nd over nd, and of course that simplifies to 1. So we've shown that for very large values of n, the ratio of any two consecutive terms approaches 1, which is surprising in a way. Now let's look at this arithmetic series. Notice the terminology. When we are summing a given number of terms of an arithmetic sequence, we refer to it as an arithmetic series. And as we developed in the first part of our series, we obtained a formula for the sum of n terms, which is given by what you can see there on the screen. And working out the sum of, let's say, the 5 terms that we have our value for the first term a equals 4, the common difference d is 3, and n is 5 because we are evaluating the sum of 5 terms. Making those substitutions, we have the sum of the 5 terms coming out to be 50. Now let's look at another arithmetic series, a very well-known one, the sum of the first given number of odd numbers, 1 plus 3 plus 5 and so on. Again, let's evaluate the sum. for a given number of terms. We have our a equals 1, the first term. The common difference is 2. And keeping n as an unknown, you can see that replacing the values for a and d gives us the expression Sn equals n squared. What that means is that the sum of the first n odd numbers is equal to the square of the number. It produces square numbers. So for example, the sum of the 4 numbers that we have on the screen will equal 4 squared, which is 16. In a similar way to the proof in the previous section, we can show that the limit of the ratio of any two consecutive sums of a series is equal to 1. We start off by using our formula for the sum of a series. You can see that Sn plus 1, the n plus 1 sum, is equal to the expression there that we have on the screen. Looks a bit complicated, but if you look through it carefully, you will see that it simplifies easily enough. Now, making the substitutions for the ratio, we have our limits, just simplifying there a little bit. Now notice that for large values of n, the values of 1, 2a, d and 2a in the denominator are negligible, so we can more or less replace them with the idea of a 0. And what remains is what we have there on the right. And you can see that the numerator and the denominator are now the same, so cancel those and we're left with 1. A neat little proof. Now here's something interesting. Did you know that the difference between the sum of the first n even numbers and the sum of the first n odd numbers is equal to n? Let's see if we can go about providing a formal proof for that. Here are our even numbers, and the formula for the sum of those will be using a equals 2, d equals 2, and capital N number of terms. Making the substitution, you can see it simplifies to n bracket n plus 1. Let's do a similar thing for the odd numbers. There they are, using the same formula for the sum, but replacing now with a equals 1, d equals 2. You can see that the sum of the first odd numbers, the first n odd numbers, is n squared. In fact, this is what we showed in the previous screen. Now what we want, of course, is the difference between them, so we can work out the expressions for the even minus the odd, and you can see it's there on the right, n bracket n plus 1 minus n squared. We can simplify that by expanding the brackets first of all, and then notice that we can cancel the n squareds and we're left with n. So we've shown that the difference is indeed equal to n. Now here's a way to impress your friends with what we've just looked at. Find a friend and ask them to, first of all, sum the first 100 even numbers. Now they can use a calculator or use the formula for the sum of a given number of terms, whatever they like, and then ask them to do the same thing for the first 100 odd numbers. Subtract the smaller from the larger answer. And this is the way they will approach that. There's the sum for the first 100 even numbers, comes out to be 10,100. There's the sum for the first 100 odd numbers, comes out to be 10,000. And the difference, of course, is 10,100 minus 10,000, which is 100. But of course, we knew the answer was 100 straight away, didn't we? We knew that the difference is going to be n, in this case 100. So we would have saved your friend a lot of worry if we had said to them straight away that the answer would be 100. A neat little trick. Let's look at something else that will astound your friends. Let's suppose you show your friend the sequence -4, 1, 6, 11, and so on. So the sequence is infinite in either direction. And ask your friend, without him or her revealing to you, a series that they've chosen from that sequence, the original sequence, with a proviso that it must have an even number of terms. For example, 6 terms, 8 terms, 10 terms, and so on. And let's suppose that this is the sequence or series, because we are now going to add them, that your friend has chosen. You ask your friend to calculate the sum of the first half of the terms and ask them to tell you what the total is. In other words, this is what your friend is working out, which comes out to be 34. Now you, in your infinite wisdom, will be able to tell your friend straight away that the sum of the remaining 4 numbers of the series is going to be revealed to them very quickly. And it will be 114. But how would you be able to do that very quickly without using a calculator, especially if there will be many terms to add together? Let's see how we can do that. Let's begin by using some notation. Let's use S1 to represent the first half of two M terms. That means, for example, if the subsequence consists of 20 terms, then M will be 10. 2 times 10 equals 20. And the formula that we will use to sum those M terms will be, as you can see there on the right. Similarly, let's use S2 to be the sum of the second half of that series. Now, what's going to change is that the second half of the series will not start at the first term of the overall series. It will start as you can see there, at the Tn plus 1 term. So we need to work out what that is, and we will do that using our Tn formula, where we replace the n by n plus 1, as you can see there. And it comes out that the n plus 1th term is a plus md. And we can replace that with the a in our formula for S2, as you can see there. Now what we're going to do is manipulate this formula for S2 to involve S1 as well. So first of all, let's simplify what's in the square brackets by expanding the brackets inside. And now just a bit more simplification. Now notice that the first part simplifies to m squared times d. And do you notice something about the second part? That's right, it's equal to S1, isn't it? As you can see by comparing it to the top line. So what do we have after all that? We have that the sum of the second half of the sequence, or the series rather, is equal to m squared d plus the sum of the first half of the terms of the sequence or series. And we can just write that in a simpler way like that. Alright, let's see how we can use that to amaze your friends or dazzle your friends. So let's suppose you have your sequence, as you can see, and you ask your friend to choose a series from that. Now, you don't know what that series is, but what he does reveal to you is that it consists of 8 terms. And when he added the first 4 terms, the sum was 192. Now we're going to use this expression that we just developed to work out the sum of the last 4 terms. The sequence has d equals -8 because the terms are descending by 8. And of course there are 4 terms that will be summed, so m equals 4. And of course we also have that the sum of the first 4 terms as revealed by your friend is 192. So let's make those substitutions. And you can see that it comes out that the sum of the last 4 terms is 64. Now this will be an especially interesting or amazing trick. Well, it's not really a trick, is it? It's mathematics, but it will be more impressive if you can encourage your friend to use relatively large n values so that m squared d comes out to be large, and it will be more amazing that you could give the answer so quickly. I hope this brief discussion of some of the properties and formal proofs of arithmetic sequences and series has been interesting and instructional, and I hope to see you soon in coming videos. Bye bye.